This video is on calculating equilibrium constants. So I'm going to show you, given some concentrations, how to calculate the actual value for Kc. So there are some steps to follow that will help you out with this. So the first step is to tabulate initial and equilibrium concentrations for all species in the equilibriums. So initial is the key here, and I'll show you how we're going to label this when we do an example. All right, so this will be, we're going to label this I, equilibrium them is our goal. We're going to label that E. All right, so 2 then is if an initial and an equilibrium concentration are given for a species, you can calculate the change. So the change we're going to label C, because lots of times we're going to need that to find the actual equilibrium. We're going to use the coefficients in the balanced chemical equation then to calculate the changes on concentration of all species. And what I mean by that is we're going to find an equilibrium expression. Then we're going to deduce the equilibrium concentration of all our species and then plug them in and calculate our actual constant. So I think this will all make more sense with an example. So you have this one in your notes packet. So the solution is prepared with concentrations of both I2 and I- equal to 1 times 10 to the negative third molar before the reaction. And if concentration of I2 changes to 6.61 times 10 to the negative fourth molar at equilibrium, what's the equilibrium constant? Okay, so we're trying to find Kc. So Kc, remember, right, our equilibrium expression is the concentrations of our products over our reactants, and any coefficients become exponents. So there's no coefficients in this. It's already balanced, so we don't have any exponents. But what we have on the top is our concentration of I3 minus, and this is all divided by the concentrations of I2 and the concentrations of I minus. All right, so we need to find those concentrations at equilibrium to plug them in. Remember, because K is the equilibrium constant. So let's go back to up here to see what we have. We have some concentrations here. Now we have the concentrations of I2 and I minus, it says, is this, but that's before the reaction. So that's at the start. So that's not equilibrium. And then we have a concentration of I2 that changes to this at equilibrium. So then this is at equilibrium. So we can use these pieces to fill in our missing pieces. So I'm going to lay this out by finding what we call the initial concentrations, the change, and the equilibrium concentrations. And I'm going to do that for each of these. So I'm going to draw kind of a little table. And lots of times we call these ICE tables. All right. So this is the one we're going to want right here. And that's what's going to then get plugged into this to solve for Kc. So if I go back up here, it says 1 times 10 to the negative third molar. That's for I2 and I minus before the reaction. That would be initial. So I'm going to fill that in 1 times 10 to the negative third for both of these. Now think about this. If that's what I have at the start, I'm adding, these are my 2 reactants. I have no product yet. Nothing's happened. Typically, you're going to find that there is usually no product to start. All right, so concentration of I2 changes to 6.61 times 10 to the negative fourth at equilibrium. So I2 is this first one, and equilibrium, it says, is this 6.61 times 10 to the negative fourth. So what we can do is we can figure out, okay, what's the change in I2? And that change is going to be the same as the mole ratio. So I can take this 6.61 minus 1 times 10 to the negative third. So that backwards. Our initial, right, it's going to go less. We're going to have less. So this is going to go down, which it does. By how much, though, is the question. So if I take 1 times 10 to the negative third and I subtract 6.61 times 10 to the negative fourth, I get a difference of 3.39 times 10 to the negative fourth. That's how much the I2 concentration decreased. That's why I have a minus there. So 1 times 10 to the negative third minus 3.34 times 10 to the negative fourth will equal 6.61. So now my other reactant concentration is going to go down by the same amount. And the reason it's the same amount is the ratio is 1 to 1. So it's the same starting value, same change, so the same equilibrium value. Okay, so here's the piece we're missing then with I3. How much did that change and where does that end up? Well, it's the same change, still a ratio of 1 to 1. But the product, right, can't go down from 0. The product's going to increase. Think about this, right? At the start, your reactants are going to turn into your products, right? We're going to be shifting right. So how much is it going to increase? That same number, 3.39 times 10 to the negative 4th. So 0 plus that is this. Okay, so now we're going to take our equilibrium values right here, and we're going to plug them into our equation to solve for Kc. So we'll do that down here. All right, so Kc equals, all right, so my I3 minus is this 3.39 times 10 to the negative 4th. And then in my denominator, it's going to be this 6.61 times 10 to the negative 4th times itself. You could do squared if you want, or you can write this also. All right, and when you plug this in your calculator, you're going to get 775 point something. I can't remember what it is. But you're going to round this to 3 sig digs, which would be 776. So this is your value for Kc. That's how you calculate Kc given concentrations in what we call an ICE table.